All right, my dear geometry students, this is lesson 9-2. It's called Similar Polygons. It is located on page 356 of your text. It is in Braille volume 33 on page 356, straight up, titled 9-2, Similar Polygons. And it starts out with the usual, what will you learn? You're going to learn to identify similar polygons and why it's important. One of the reasons is it's used in construction to use drawings that are similar to the actual building. They're called blueprints. But down towards the middle of the page in Braille, very top of the page in print, it starts out with a paragraph of information, page 356. So it says a polygon is a closed figure in a plane formed by segments called sides. It is a general term used to describe a geometric figure with at least 3 sides. That's our triangle, right? We study triangles and quadrilateral, 4 sides. Poly means more than 2. Polygons that are the same shape but not necessarily the same size are called similar polygons. The 2 triangles shown are similar. For naming similar polygons, the vertices are written in order to show the corresponding parts. The symbol for similar is a tilde, and it is a dot 4 and then a 1, 5, 6. That's 1 tilde. So they show you an example on the next Braille page, 356A, at the very, very top. Has a shape indicator T for triangle, and then capital R, S, T, and then the similar symbol, 1 tilde, a dot 4, and then a 1, 5, 6, and then a shape indicator T, triangle, capital V, capital W, capital X. So it reads triangle RST is similar to triangle VWX. And as the paragraph before said, the vertices are written in the same order as they correspond to each other. So we have RST, the first letter R corresponds with the first letter of the second triangle, V. You have VWX. So R corresponds with V. The second letter, S, corresponds with the second letter of the second triangle, W. So S to W. And then T, the last letter of the first triangle, corresponds with the last letter of the second triangle, X. You can also use the same symbols, the way they write this out, to write corresponding sides. So R to S, 2 endpoints, right? Create a line segment or a side. So RS, the first 2 letters, correspond with the first 2 letters of the second triangle, VW. The second 2 letters, ST, correspond with the second 2 letters, WX. And then the outside letters, RT of the first triangle, correspond with VX of the second triangle. So you can use the givens, the symbols, to help you know which angles correspond with each other and which sides correspond with each other. And that's really important to be able to figure out when you're working with similar triangles, because we have to have corresponding angles congruent to each other, and we have to have corresponding sides proportionate to each other. That's what we're going to learn in the definition of similar polygons here in a minute. There's a drawing down below, a tactile. It has a small triangle on the left and a bigger triangle on the right, and in between, going from each vertex on the small triangle is a heavy line arcing with an arrowhead to the corresponding vertex of the larger triangle. So if you're at the top at vertex T on the little triangle at the left, there is an arrow that's showing it goes to the vertex that it corresponds with, X, on the triangle, the big triangles next to it. And then if you go back to the little triangle to the bottom left, we have point R, vertex R, and there's an arrow going from, an arcing arrowhead going from vertex R to its corresponding angle vertex V on the large triangle. And then you go back to the small triangle and find vertex F at the bottom, or excuse me, S at the bottom right. It has a line, an arcing arrow line pointing to the vertex W on the big triangle. So it's showing that corresponding, these, you're being given that these two triangles are similar with that tilde between them. Triangle RST is similar to triangle VWX, and then it's showing you with arrows vertex to vertex. But one of the ways to be able to figure this out is if they give it to you in writing, you can just use that trick to go letter for letter in the same order. If they don't, then you do have to figure it out based upon the drawings. Now down below these two similar figures, these two similar triangles, they point out corresponding angles, and there's another new Braille symbol possibly for you. It's the corresponding symbol. In print, it's a little arrowhead. In Braille, it's a shape indicator with a little mini kind of number line. So we have shape indicator angle, an OW. Angle R corresponds with angle V, and the corresponding is a shape indicator ED, an OW, two colons, and an O. And then you get shape indicator OW again for angle, and then V. And so that reads angle R corresponds with angle V. And then the next one says angle S corresponds with angle W, and then angle T corresponds with angle X. And then below that it talks about the sides. And again, you can figure out these sides by the drawing, or you can figure them out from the very top where it said triangle RST is similar to triangle VWX. They do the first two letters. RS is corresponding to VW. Notice they do the line over indicator, so they do a .5, capital R, capital S, a 126, and then a 156, and then an ER for line over. And then, so that means side RS, and then corresponds your ED with your OW colon colon O, and then a .5, capital V, capital W, and then 126, 156, and ER for a line over that. So side RS corresponds with side VW. The next line reads side ST corresponds with WX, and the next line side TR corresponds with XV. You could also say RT corresponds with VX if you want to write them in reverse. Next page, some important information to recall. It reminds you to read the symbol, the tilde symbol, as similar to, and then it says recall that in congruent figures, corresponding angles and sides are congruent. In similar figures, corresponding angles are congruent, and the measures of corresponding sides have equivalent ratios or are proportional. So that's why we reviewed ratios and proportions the previous section, was so that you could practice it with similar figures. So they have the same ratio or proportional. So that brings us to the official Euclidean definition of similar polygons on the next page, 356C. Let's read the words, and we'll look at the tactile, and then we'll read the symbols. So the words say definition of similar polygons at the top. It says two polygons are similar if and only if their corresponding angles are congruent and the measures of their corresponding sides are proportional. So there's two criteria that have to be met in order to say two figures are similar. You cannot say they look similar. You have to do the math and figure out if they meet both criteria. First criteria, are all the angles congruent? If they're not, moving on. This one's out. It's not congruent. Then, if it does meet congruent angles, then you have to check the proportionality of the sides. Do they have the same ratio? And if they do, it meets both criteria, and you're able to say the two figures are similar. There's some sort of scale factor going on between the two figures. Something is a certain amount larger than the other figure. So we have in a model, we have two quadrilaterals. Don't be fooled. These are not parallelograms. They sort of kind of look like a parallelogram, but they are not. They do not have opposite angles congruent. or opposite sides congruent, but they are showing congruent angles between the similar figures. The bottom left-hand corner is A on the first figure, and it has one congruency arc. The figure to the right, the bottom left-hand corner, is E, and it has one congruency figure. So A is to E. A corresponds to E. The bottom right is B, and it has two congruency arcs, and it corresponds with the bottom right F of your figure to the right. The top right of the left figure is vertex C. It has three congruency arcs at that vertex, and it corresponds with the top right G of the figure at the right with three congruency arcs. And then we move all the way over to the top left at vertex D on our left-hand side figure. It has four congruency arcs. And in our right figure, we have vertex H with four congruency arcs. So A corresponds with E, B corresponds with F, C corresponds with G, D corresponds with A. So we would write them in that order. A, B, C, D is similar to E, F, G, H. Just so happens that they're alphabetical. Sometimes that's not the case. You could also do AB. Side AB corresponds to EF, the bottom sides, correct? BC, the right-hand side, corresponds with FG, the right-hand side of your right figure. CD corresponds with GH, and DA corresponds with HE. Down below the drawing, it gives it in symbols. It shows the proportions in that corresponding order. AB over EF equals BC over FG, which equals CD over GH, which equals DA over HE. So all the sides are equivalent ratios to each other. We could switch them around. We could say AB over EF equals DA over HE. Doesn't matter. They all equal each other. They're all the same ratio. So that's one criteria. And the second criteria is that angle A is congruent to angle E, angle B is congruent to angle F, angle C is congruent to angle G, and angle D is congruent to angle H. So all angles are congruent, all sides are at the same ratio, they are proportionate, so therefore these two figures are similar. So down in symbols, it says polygon ABCD similar to polygon EFGH. Notice they vertex to vertex is in the same order. A, E, B, F, C, G, D, H. And then you could do it in order for their sides. AB, the first two letters of the first one, corresponds with EF, the first two letters of the second one. BC, the second two letters, corresponds with FG. And then CD corresponds with GH. And then your outside letters, AD to EH, or vice versa, DA to HE. You're going kind of clockwise or counterclockwise around it. All right, so let's go practice using these rules on a couple of examples. Number one asks us, determine if the polygons are similar and justify your answer. And you can't just say, well, they don't look like it. You have to justify it as geometry attorneys. So it is a no-brainer. We look at these and we notice we have two parallelograms, but one is a rectangle and one is just a parallelogram. Notice that your rectangle on the left has 90-degree angles. Your parallelogram at the right has a 60, a 120, a 60, and a 120. So angles are not congruent. So therefore, these two figures are not similar. You have to meet the criteria of congruent angles to be similar. The sides are proportionate. 5 is to 10 is 4 is to 8. That's proportionate, isn't it? But it has to be both. So these are not similar. These polygons are not similar. And that's what it says down at the bottom underneath the drawings. Since 4 is to 8 equals 5 is to 10 equals 4 is to 8 equals 5 is to 10, the measure of the sides of the polygons are proportional. However, the corresponding angles are not congruent. The polygons are not similar. So in the your turn, you have two that look like potential parallelograms. The first one has opposite angles that are congruent. The top left has a congruency arc. The bottom right has a congruency arc. The top right has two congruency arcs, and the bottom right has two, or bottom left has two congruency arcs. And they join all those vertexes to create this what looks like a parallelogram, because the top side is 5 and the bottom side is 5 and the left side is 4 and the right side is 4. So your parallelogram knowledge should kick in. Congruent sides and congruent opposite sides are congruent and opposite angles are congruent. So we immediately go to the figure at the right, and the corresponding angles are also congruent. The top left has one congruency arc. The bottom right has one congruency arc. The top right has two congruency arcs, and the bottom left has two congruency arcs. So those match up one for one, left-hand corner to left-hand corner, right-hand corner to right-hand corner, bottom left to bottom left, bottom right to bottom right. So we meet the congruency criteria that angles have to be congruent. Now let's check out our sides. So we have a 7 and a 6 and a 7 and a 6. So again, we know we have a parallelogram. So 5 is to 7, that top side to top side, as 4 is to 6. So we want to check that out. 5 is to 7 as 4 is to 6. So you would braille out or write out 5 is to 7, 5 over 7, does that equal 4 over 6? And you would check by cross multiplication. Well, 5 times 6, the extremes, the outers, is 30. The inners, the means, 4 times 7 is 28. 30 does not equal 28, so therefore this is not proportionate. So even though they sort of looked like it, they are not similar because the sides are not proportionate. The next one below little letter A is little letter B. It looks like we have two right triangles, a small one on the left and a larger one to the right. They're right triangles because they have that right angle indicator in the bottom left vertex of each one. So we know we have one angle that's congruent, but we got to have all of them. So let's check the top left vertex. There's one tick mark. And on our big triangle to the right, there's one tick mark. So we have another angle that's congruent. And then the bottom right-hand corner has two tick marks, and the bottom right-hand corner of the right one has two tick marks. So they have congruent angles, so we meet that criteria. Now we find out if all the sides are proportion. So 3 is your left side to 6, right? So we write 3 is to 6, or 3 over 6. Does that equal 4 over 8? 4 over 8. And does that equal 5 over 10? So you should see that all of those reduce to 1/2, don't they? So they do equal each other. 1 over 2 equals 1 over 2 equals 1 over 2. But we could cross multiply. 3 times 8 is 24. 4 times 6 is 24. That works. 4 times 10 is 40. 5 times 8 is 40. 3 times 10 is 30. 5 times 6 is 30. You do all the cross multiplication, and they all equal each other. These are similar figures. They are proportionate. So turn the Braille page to 357B. And if we know several measures of two similar figures, we're allowed to find the measure of the missing part. This is where we use our solving proportions techniques and our algebra techniques, and we can find missing variables if we're given that they're similar. So this example 2, says find the values of x and y if triangle RST is similar to triangle JKL. So we're given that they're similar, so we don't have to meet any criteria. We already know they're similar. So now we're going to try to find the missing pieces. So RST is the top triangle. R is the top, S is the bottom right, and T is the bottom left. and from R to T is 4, from R to S is 5, and from T to S is 6. They say that's similar to the triangle down below, JKL. That's what they told us. That's what they gave us. So we know just in writing, RST is similar to JKL. We know R goes to J, first letter to first letter. S goes to K, second letter to second letter. And T goes to L, third letter to third letter. So from J to K is X. From K to L is Y plus 2. And from L to J is 7. So we're able to set up our corresponding sides and use substitution and figure out what the missing pieces are. So they do that on the next page. They say write a proportion that can be solved for x. So first we want to use corresponding order for the vertexes to write the proportions. So RS over JK equals ST over KL, which equals TR over LJ. First two letters over first two letters. Second two letters over second two letters. Outside letters over outside letters. Then that's the definition of similar polygons. That's the reason why we can do that. This is a little simple proof. Then we use substitution. So for RS, we look back on our drawing and RS is 5. So we plug in a 5 for RS. JK is X. We plug in an X for JK. ST is 6. We plug in a 6 for ST. Y plus 2 is KL. We plug in that for KL. And then 4 is TR. And we plug in that for TR. And then 7 is LJ. And we plug in that. So we have this 5 over X equals 6 over Y plus 2 equals 4 over 7. So then we write out the proportion and we solve it. We can bounce around. We make 5 is to over X equals 4 to 7. We're going to use that. We're going to use that 4 to 7 each time. So we cross multiply. 5 times 7 is 35. That equals 4x. We divide both sides by 4. 4 goes into 35 4 times with a remainder of 3, so it's 8 3/4 for x. If you turn to the next page, Braille page D357, we're going to solve for the other side. 6 over y plus 2 equals 4 over 7. We still use that 4 over 7, but now we're going to solve for y. So we cross multiply. Outers, 6 times 7 is 42. And inners, 4 times y plus 2, we need to use the distributive property. So 4 times y plus 4 times 2 is 8. We use our subtraction property of equality and subtract 8 from both sides. We get 34 equals 4y. Divide by 4 on each side using our division property of equality. And 4 goes into 34 8 times, remainder 4. So that, or excuse me, remainder 2. So 8 2/4 is 8 1/2, and that is what y is. All right, so we use a little bit of algebra to solve those. The next problem has a your turn to find the values using the same process. I'm going to leave that to you to check that out and see if you can do that. You have a triangle ABC is similar to triangle DEF. Pay attention to the way they wrote it. A to D, B to E, C to F, AD, right? AB to DE, BC to EF, AC to DF. You can use the triangles to find all the measurements that you need, and this is a decently done tactile that this is pretty easy to make out. Down below this, it's new information about scale drawings. They're often used to represent something that's too large or too small to be drawn at actual scale. Contractors use scale drawings called blueprints to represent the floor plan of a house to be constructed. The blueprint and the floor plan are similar. So this was on the next page. Number 3, it says, in the blueprint, 1 inch represents an actual length of 16 feet. So for every 1 inch on the drawing, it's actually 16 feet in real life. So this way somebody could take a ruler to the drawing and put it down there and go, oh, this is an inch, so I need to go 16 feet on the width of this wall or floor or wherever we're working. If it's 2 inches, I need to go 32 feet. If it's a half an inch, I need to go 8 feet. So it's a 1 to 16 scale factor. So on the blueprint, they want to know what the dimensions of the living room are. So there's a blueprint on the next page. It's kind of crazy to make out. But if you start in the top left corner, it's this big kind of rectangular shape a little bit all the way around, and then inside there's quote-unquote the walls. The left-hand corner, they're labeling that room the dining room. The middle is the kitchen, and then the far right room is the utility room. Then below that is the garage, and then next to that on the left in the bottom left-hand corner is the living room. The dimensions of the living room at the very bottom are 1.5 inches, and to the left, they put that down at the bottom also, is 1.25 inches. So you need to solve the proportion 1 is to 16 as 1.5 is to x, and 1 is to 16 as 1.25 is to x, or y, or however you want to do it. So this is just straight up multiplication. 16 times 1.5 equals x. So we need 16, and then half of 16 is 8, so 24 feet. So 1.5 inches is 24 feet. That's a pretty sizable length of a living room. And then 1 inch to 16 feet equals 1.25 inches to how many feet? So we multiply 16 by 1.25. We're going to get 16, and 1/4 of 16 is 4, so we're going to get 20. So the next measurement is 20. So the actual dimensions will be 24 by 20. All right, so that's it for 9-2. I'd highly recommend that you do the check your understanding, at least do number 4 through 7 for extra practice. You can do number 9 through 25, almost 27, 9 through 27 for extra practice. It's really good to look at the different tactiles and to decide, do they meet the criteria of congruent angles and proportionate sides. And then use your definition of proportionate, your cross multiplication techniques, you're multiplying the extremes and the means and making them equal to each other and solving for the missing variable. And that should get you through this section. So that's the end of 9-2, similar polygons. Do good thinking. We'll see you in the next video.